Good morning, class. I guess everybody's enjoying their cooler weather, or I hope you are. It's certainly a big change. We get up in the morning and it's in the 40s. So I guess we'll have our little entry into the fall winter type weather for a week, and then possibly next week it'll get warmer. Who knows? But that's the life of living in the Houston area. So if this is a good thing for you, uh, I'm happy for you. And if not, as they always say, the weather will change soon. I've learned that to be the case in the Houston area. So what we want to do today, remember, I'll have the announcement about the test that we'll have next week. We want to cover some additional information about inverse trig functions as they relate to the triangles. So what you're seeing is that there's really no difference in the arithmetic and in the computations that we do with the trig functions when it comes to either a t-value measurement on the unit circle or the actual abstract idea of the associated angle. The reference number, the reference angle, all the arithmetic is exactly the same. The Pythagorean identity is exactly the same. And so we have the additional plus of having the interpretation of the right triangle. And so that adds new ideas to what we can do with trigonometry. So we want to kind of remind ourselves of some of those ideas today. So first, like I said, let's start with the inverse trig functions and look at some new ideas that we have, and then segue into the law of sines, which I think you'll enjoy. One thing that we have is a support tool to what we're doing when we need the good calculus approximations. We can use our Google calculator. Sometimes I have students use tables of tabulated trig values, and those are good and fine. But that adds a layer of additional time, which can be good. But since we're in the virtual setting, I think the Google calculator will give us a little bit more efficient means of getting a good approximation. Then again, of course, when you get to calculus and see the infinite series, you'll understand why I always say the calculus approximation. So let me go ahead and share my screen. So when we begin with the inverse trig functions, or when we began with them, we set them up based upon the unit circle. And so what I want to do is just to kind of recap. So this is 6.4, and I'll just say inverse trig functions again. We'll throw in the inverse trig functions every time we have something new to add. But everything we did before will still be valid. So we'll just say inverse trig functions again. Now what we can do in this particular case is just go ahead and write down what we've learned. Now I'm going to focus on 4 of the inverse trig functions, basically because that's what we're going to spend most of our time on in calculus in the rest of this class, even though you have all 6. So I just want to remind you of the inverse sine. We'll use an independent variable of x. Now, remember, we have the inverse equations, which I have written down a million times, so I won't do that again. But what we're going to do, as you've seen in your WebAssign, is just write down the corresponding equation. If we apply sine to both sides, this just says that x equals sine y, just like with the logarithm equations. And we know with the inverse equations that you did in section 5 of chapter 5, this is true with the restricted domain, x in -1 to 1, and y, which is the inverse trig function, that lives between -pi/2 and pi/2. So again, these are things you need to know. If you know the graph, then you know this automatically. So there are ways to keep these in your brain. The other one that we use, even though the calculus is very similar to this, is the inverse cosine. And of course, we can just apply cosine to both sides and of course absorb here. Again, the inverse rules, we just get x equals cosine of y. And then, of course, as we know, the restricted domain, -1 to 1. And then the way we restricted the domain, we get that the inverse cosine lives between the two real numbers, 0 and pi. So that was our second inverse trig function. And then the third one that we'll spend some time with will be the inverse tangent. So again, like we have with the inverse rules, apply tangent to both sides and use the inverse rule to just get x. And then, of course, tangent of y, we write symbolically this way. So we're seeing that the symbolic computation and writing is really how we move to the next level in mathematics, and we continue to do it. So now, of course, this function is very user-friendly. I'll just write x as any real number, -infinity to infinity. And then, of course, the output, the inverse tangent function, lives between the two horizontal asymptotes, -π/2 and π/2. Again, a very important inverse trig function. All of these will have more importance as you move into Cal 1 and Cal 2. And then the last one was the kind of the interesting function, the inverse secant function, again, which utilizes, unfortunately, not always a universal domain. Unfortunately, like I say before, there are two that float around, and no one has decided which one's going to be the most formal. But the one that I'm using is I think, maybe considered more so. So let's apply secant to both sides, and that'll give us x equals secant y. And then, of course, now we knew that we have the x running 1 or greater and -infinity up to -1. So we could write that with the absolute value like this. Now we can actually do that and know what it means. So we 1 to infinity, -infinity to 1 using the disjunction. And then now the output will complement what we have here. And that's the reason that this is a good use, because we get some nice reciprocal identities. And then, of course, we have the identities for the negative inputs. So all of these things you need to know. So, of course, this will go 0, π/2. Omit the π/2. This becomes a horizontal asymptote in the graph, and then π/2 to pi. So these are the ideas that are important for us. And now you're thinking, so why do we revisit these, Professor Ron? You know what? You know, this is stuff we already know. But now, let me adjust this just a little bit. I like to have the paper just so on the desk, and then of course I bump into it and it messes it up. What we want to do is think about, okay, so if we can go in the reverse path, we can have a way with these ratios of sides of triangles to be able to go in the reverse direction and compute angles. So the idea here is that now we have an additional dimension. We already had it before, but since we like to work problems with triangles, it's really nice to have this particular or additional layer of content. So let's look at an example of this. And this is, you know, not very difficult, but I just want to give a very simple example. So let's draw a right triangle. So we're working a problem. And what I'm drawing here is, of course, a right triangle. It's going to have a right angle. Again, our drawings can tell us basically what's going on, but the way we label them mathematically has to be consistent. So you can put any kind of label as far as numbers go, but mathematically it might not make any sense. So here we'll take our acute angle theta to be this one here, and we're going to be given, in this particular case, that the hypotenuse is measurement 51. The leg adjacent to theta will be 24, and then the leg opposite will be 45. Now, this is very simple in the sense that I just simply want to define the trig functions for all of these particular values, and then move into the inverse realm. So what WebAssign does is they say, let's compute sine, tangent, and cosine of theta. So let's write that down. So sine of theta and tangent of theta, we'll just write them down, and cosine of theta. So this will be opposite over hypotenuse. So we're thinking this at least in terms of radian measure or degree measure, depending on how we want to interpret it. When we work a problem, we have to, if we're going to use the conversion with the Google calculator, we have to pretty much put in context what kind of theta we have. Is it the pure measure radian or the pure measure in degree? And then tangent will be opposite over adjacent. So this will be 45 over 24. And then the other situation, and of course you're thinking, well, wait a minute, I'll go ahead and reduce these later, but let's just go ahead and now get the cosine, which will be adjacent over hypotenuse, which is 24 over 51. Now, of course, WebAssign doesn't care if you don't reduce, but we can reduce here. We've got a 3 in both of these. So this one will give, when we divide in this particular case, that'll give us a 15. And then a 3 here, that will be a 1 and a 21. So a 15 over 17. Let's keep going. A 3 here will give us a 15, and a 3 here will give us an 8. Again, very simple, but clearly you don't have to do this, but I factor everything to death, so we do it anyway. So divide by 3 here, and then 3 here gives us a 17. So we get these ratios in reduced form, all of these being relatively prime. And so now we basically have 3 definitions of theta. So we look at this and say, okay, well, if we were interested in making sure that we had solved this triangle, then we can do the reverse path. That is, we can say, okay, well, we can go these angles here. If we go back up here and say, okay, where does inverse sine live? Well, these are positive inputs. And so we're going to see that the inverse sine will give us an acute angle between 0 and pi over 2, or 0 and 90 degrees. We go to the inverse tangent. Again, we have a positive input. So we see that the theta would be an acute angle between 0 and pi over 2. And then for the cosine, the same thing. We're going to have 0 to pi over 2 because the input is positive. Of course, if it's negative, it's going to run over into the second quadrant. Again, pi over 2 to pi. So these constructions here basically tell us what we should expect when we apply the inverse trigonometric function. You don't just throw caution to the wind and say, well, whatever I get, I guess that's just what the calculator told me. You're already going to know what you're going to get. The calculator will just give you a more precise approximation. So now if we like, we can say theta is the inverse sine of 15 over 17. Theta is the inverse tangent of 15 over 8. And of course, in the WebAssign, they would put in the parentheses for you. I don't have to put them here because it's clear what I mean. And then theta is the inverse cosine of 8 over 17. So if you're solving a triangle, you can use any one of these to actually get a calculator or calculus approximation of the angle. So, you know, heck, it doesn't really matter. All of these we find on our Google calculator. So if you like, let's just go ahead and use, I don't know, let's use the inverse cosine. So now what we're going to think of, just to remind ourselves, say we've got a client that wants the angles in degrees, and so we could do the use radian measure and use the 180 over pi conversion factor. We can do that. So let's do that just to practice. So if we wanted theta in degrees, we could do here, let's use the cosine. We'll have inverse cosine of 8 over 17 where this is processed in the radian mode, and then we would do the conversion. This would give us 180 over pi, thinking of that in terms of degrees. Now, this would be a calculation that we were doing if we weren't using a degree mode, excuse me, on our Google calculator. So let's go to that and just compare what we can do. So I'll see if I can find my, it always is tough to find this Google calculator. Let me just move this down. Let me get rid of that. And let's see here. Pull this back up. Again, it's not a bona fide web page, and so it doesn't always get seen by the Zoom. I have to just, let's see here. We've got almost. So let me try one more time. Let me move this here. Now it sees it. I just have to put it in the right place so it sees it. So here's my Google calculator. Again, I wish this were just a bona fide web page, but since it's on the search page, it doesn't like to see it as easily. So now we can look at our calculation and just stay in the radian mode and do inverse cosine. So remember, the other symbolism for inverse cosine is the arc cosine. So at least the Google calculator reminds you of that. And so we'll have 8 divided by 17, close this out, and then multiply by the conversion, 180. Well, I'll just do it this way. Let me just go ahead and put this in parentheses so it looks cleaner in your notes. Divided by pi. And this gives us 61.9275. So for instance, if we were doing a problem and we wanted to round to 1 decimal, say WebAssign said round to 1 decimal, this would give us 61.9 degrees. Now, let me just show you something else. Say for instance, we just said, okay, well, we're gonna go ahead and assume that we're in the degree mode. So you could go to degree mode and then not have to worry about the conversion factor. So the idea is if we were in degree mode and we do inverse cosine, and then we'll have 8 divided by 17, this will automatically do the conversion for us, and we get the same response. So it just depends really what kind of calculation you're doing and how you move your arithmetic forward. It just needs to be clear. So again, when you look at what I've written here with the problem, I just basically assumed that I left my calculator here in radian mode and then did the conversion here to degrees, so I was sure to get this. Or you could just forget this, like I say, and just put your calculus approximation in degree mode. So of course, we could use any one of these. And of course, here's the approximate acute angle that we were promised by our arithmetic up here, or our inverse trig functions. So again, when you take your physics and you take your other classes, use your mathematics from pre-calculus to make sense out of what you're doing and make good choices so that your work is consistent. Don't get sloppy in your non-math classes just because, well, the professor said I could use a fancy calculator so I can turn my brain off. You don't want to do that. Now, another thing that we can do with the calculations, and this has to do, like I've just said before, with solving equations. So if we're interested in actually solving equations, let's look at a situation. Notice here, these are all equations. And for instance, if I were simply interested in finding all of the possible solutions from 0 to pi over 2, we have them because these functions are one-to-one. But if I extend the set to encompass a larger interval, then I'll have to make some adjustments. That is, the inverse trig function gives me one output, it's one-to-one. So maybe the problem wants me to find solutions that live between 0 and 180 degrees or 0 and pi radians. Then I'll have to say, okay, well, the inverse trig function gave me one answer. And if I'm using any of these functions, that one answer will be an acute angle. And then the other one, I'll have to figure out, well, do I have another one in this case? Am I going to get an additional solution with the remaining inverse trig functions? I'll have to think about that. So that's why knowing this is imperative. And then actually knowing the arithmetic of the unit circle is important. Otherwise, you just kind of, running through the math course with blindfolds on, and I don't want you to do that. So let's look at an example from the WebAssign. So this is actually going to be a Professor Ron's lemma when we finish with it. So here's an example. And we can use the inverse trig. So in this particular case, let's see, let me start out with one that maybe is a little bit simpler. Yeah, we can do that one. Let's see here. Let's start, well, yeah, let's do this one. Let's start out with one that's kind of simple, and then we'll move up to a more complicated one. So for instance, what we want to do is compute, and I'll write this in degrees. So I want to find a theta, all thetas between, let's just say, 0 degrees and 180 degrees, such that, in this case, cosine of theta equals 5/8. Now the thing that we look at here is we have to decide, okay, this encompasses the first two quadrants, okay? And so we're thinking, in quadrant 1, cosine theta or x is positive. In quadrant 2, the cosine theta or the x is less than 0. So if we're looking for a solution here, we would know that there would only be one, because in the second quadrant, the cosine is negative. It's clearly positive here. So we're like, okay, we're done with this. We don't even have to think about it. So we think about how we've defined the inverse cosine. And even before we do the problem, we only know that to expect one solution. And here's the beauty of this problem. This is tailor-made to the inverse cosine, because the 0 to 180 is just 0 to pi. And that's the range of the inverse cosine. So we know there's only one value. So we didn't go outside the range of the cosine, inverse cosine function. So we're like, okay, even if we got sloppy and only thought there was one, it would only be guaranteed to be one. So that's what I'm talking about. If you don't know this, then you don't know the inverse trig function. So that's why I keep saying, even though this seems dry and boring, it is essential. It is absolutely essential if you want to understand how to use the inverse trig functions. Now, so what we want to do, of course, that we get a little freezing occasionally because everybody uses the internet at this time of the morning. I'm grateful to Xfinity, but nothing is perfect. So I just have to realize that we do what we do. So now we're just like back to the last problem. So equivalently, we know there's one solution. Theta will now be the inverse cosine of 5/8. And so in this particular case, if we think about this, let me write this over here. We can do this just like we did the last problem. We can write this where we assume this is in radians and do the conversion, or we can just say, okay, well, we're going to just use the degree mode on our calculator. So now we can just say degree here, And we can think just like we did before. We can do the conversion factor, 180 degrees over pi, like this, or use degree mode. You always have this choice. Now, last class we used degree mode because it was more convenient for our calculation, but I want to use this opportunity to show you exactly what your calculator, the Google calculator, is doing for you. So now when we go back to here, let's go to our Google calculator. We can do the same process. So we'll go ahead, let's just go back to the radian mode and use our conversion factor. So we'll have inverse cosine. I know I'm doing the cosine again, but it's fine. Inverse cosine, 5 divided by 8. Close this out and then multiply by the conversion factor, 180 divided by pi. And this will give us 51.3178. And if we round to 1 decimal, so I'll just say round to, in this particular case, you were asked to round to 1 decimal in the WebAssign. So this gives us 51.3 degrees. So again, just like we did last class, you can go ahead and utilize the degree mode and not have the actual factor. Let me show you again, this is very important. You can use the degree mode and then don't worry about that, or stay in radian mode and then do the conversion yourself. So a lot of times, like when we were doing the problems in the previous class, we had tangents of the 32 degrees and the 35 degrees, and it was more convenient just to use the degree mode. So the Google calculator did the conversion for us. So I just want you to see that what you're doing, you have control over, and it helps you to understand how we toggle between the degree measure and the radian measure. Now, there's one other example here that I want to share with you. And it's an interesting example because now we have to think a little bit more. This is so with the cosine function, there's going to be a Professor Ron's lemma, and I will share with you that particular result. But first, let's go ahead and look at another example. Say we have theta is going to live between 180 degrees and 360 degrees. So we're thinking about triangles, but we're not really thinking about triangles. We're just thinking about a problem because no triangle, Euclidean triangle, will have measurements here. But this is just a general problem. So we're thinking, okay, pi to 2 pi radians, basically, 180 to 360. And we want such that, what do we want? We want all theta. We don't just want, we don't want like, okay, well, throw caution to the wind and we'll be done. So such that sine theta equals -4/5. So when we look at this and we think about, well, what's the inverse sine going to give us? So now we know that for x between -1, just remind ourselves, -1 and 1, the inverse sine lives, well, we need an argument. That would help. Inverse sine with no argument lives between -pi/2 and pi/2. So now this is negative. So we know that the answer that we get here will live between -pi/2 and 0 because this input is negative. So again, that says, okay, that's going to be 1. But then we're thinking, okay, so we think about this and well, let's just say here, 180 degrees to 270 degrees, and then 270 degrees to 360 degrees. Okay, in both of these cases, the sign is negative. sine theta is less than 0. Sine theta is less than 0. So when you look at this, you're thinking, okay, well, if I have a negative angle here, I'm going to be moving counterclockwise, and that's going to throw me in the fourth quadrant. So here, this is the third quadrant, and this is the fourth quadrant. So that negative angle will correspond to an angle, counterclockwise angle in the fourth quadrant. So that's what the inverse trig function will give me. But then I have to say, okay, well, in this range here, we also have a value of sine in the third quadrant that's going to correspond to this one that the inverse trig function did not give us. So this is where we have to think about how we've defined the sine function. We don't have this happening with the cosine function, because as you move from 1 to 2 or 3 to 4, the sign of the cosine function changes. So you don't get that overlap in that direction like we do with the sine function. So now we're thinking, okay, well, let's see if we can get this one and make an adjustment to it and then figure out what this one would be. So now, for instance, here, we look at this and say, okay, well, we have sine of theta equals negative 4 over 5. And so we have theta will be the inverse sine of negative 4 over 5. Well, of course, we can use the fact that the inverse sine is odd, so we can factor the negative. I mean, if you like, I mean, maybe that makes it easier for you. So we just get inverse sine of 4/5. Just go ahead and dealing with the negative. So I'll go ahead and put parentheses there so you know, just don't get involved that with the negative. That means the inverse function, as we well know. So now when we look at this, we're thinking, okay, this is in the fourth quadrant, but it's not here. It's not a positive angle. So this is in the fourth quadrant based on what we just said. So in order to get the theta here, I would have to add 2 pi or 360 to put it to a coterminal angle that would live in here. So this implies our particular value, we'll just call it, now we can just call it, you know, alpha if you want. Alpha will be this here, and we'll go ahead and assume degree mode. This will be 360 degrees added to this minus inverse sine of 4/5. So this is where we're going to use degree mode. So we're doing a little adjustment here. Maybe I should call this a different label, and you know, because these are different angles, but I don't want to call it the same. You can just say that, so not to make you think I'm just making up something, just think this implies that we need this angle here. Let me go write it this way so we don't have an additional letter, and just say this will also live in the fourth quadrant, but it's going to be here between 270 degrees and 360. So that will be the angle that we want. And so now let's go to our Google calculator. I told you the inverse trig functions are our friends. So now let's just do it. Okay, degree mode, make sure you have the DEG. So we'll have 360 minus, go do the inverse. So click that and sine, inverse. So we got the arc sine, and then we have 4 divided by 5 and close that out. And that gives us the angle that we need. That is, this equals 306.8698, etc. So we're going to, in this case, we'll round to 1 decimal. Sometimes we'll do more, round to 1 decimal. And so this will give us 306.9 degrees. Now, what we want to do here is think, okay, well, where is the other one? Because now if we think about what we're doing here and we think about where does the other one actually live? Because we know that the sign here is the same in both cases. So how can we characterize the other value, in this case, of theta that lives here relative to this one? So what I want to do is think about, okay, so how do we get the relationship? Because right now you're thinking, I'm not so sure, Professor Ron. I could kind of try to intuit it and look at the unit circle, but that's not very good. So here's a question. Oh, sorry. Let's go back here. I'm going to leave that calculation right there. So now we think, okay, how do we compute theta that lives here? Because we know we're going to get a value over there by the symmetry of the unit circle, circle. So we're thinking, how do we do that? Well, let's just do a little computation here. So notice, I'm just going to draw a little unit circle here to give us a little recipe here, just a freehand unit circle. And say we think about having here, I'm just going to say we've got this value and this value, which have the same y value. So I'm going to do a little visual here. So this will be in the third quadrant. This will be in the fourth quadrant. And so we have an equation, sine x, I might need a new pencil, equals b. Let's see, I still have ink in this one. Yeah, I have ink. And that's the equation here. And so we have two solutions. We have two solutions. I'll just call them alpha and beta. Alpha and beta. Okay, so now we're thinking, so this means if and only if sine of alpha equals b and sine of beta equals b. We got two solutions. So we can think of this one, let's just do this one here, will be the alpha. Just doing in the counterclockwise, and this one here will be the beta. So then we're thinking, okay, well, what's the reference? So in this case, we have alpha bar, which lives in the third quadrant. Well, in this case, just be what? Alpha minus pi, and beta hat lives in the fourth quadrant, so its beta bar, so to speak, will be 2 pi minus beta. So what's the relationship here? So we look at this and say, okay, well, so if and only if and what's interesting about this is that, and I have something here I want to share with you. When you look at this particular calculation here and you say, okay, well, this is my reference angle for alpha, and here's my reference angle for beta, how does that impact any of this? That is, so now when I actually solve this equation, this if and only if what? So we've got sine of alpha equals the negative of the sine of alpha minus pi. That's using the reference number, because in this third and fourth quadrant, the sign is negative. And then we have sine of beta will now be the negative of sine of 2 pi minus beta. So if we look at all of these and say, okay, well, what's the relationship, so to speak? So we're thinking, I don't know, I've got something here I want to share with you that will make this seem a little bit simpler. So what we want to do is look at, for instance, the way I've set this up and make it look a little bit more cogent. So if I think about this and I think about what the situation is, for instance, I did this scratch work here before we started class here, and I called this Professor Ron's lemma. So I did the same thing that I did here. And notice here, when we have alpha in the fourth quadrant, using whatever letters, we have 2 pi minus alpha, which is going to be, in this particular case, the reference number in the first quadrant. But then we've got the same reference number for the other angle like I have here. So that's really my logic here. So let's do that. So now notice these two reference numbers are equivalent. I don't want you to think I'm making it up. So these reference numbers or reference angles are equal. And so now we have alpha minus beta equals 2 pi minus beta. And then if you like, we can, I don't know, we can just put things on two sides. So we have, take the alpha over. So alpha plus beta equals 3 pi. So that's the connection between these two particular setups here. So now let's just go ahead and use the notation I have here to set up Professor Ron's lemma. So now if we're thinking this is in the quadrant here in the fourth quadrant, that corresponds to our alpha. So this implies the other solution. So we'll say remaining solution is, and so now here we can think about this. So we've got beta is here. So we'll say alpha will just be 3 pi minus beta, or if we think in terms of degrees, 360 plus 180, that's 540 degrees, minus beta if we're in degree mode. So here this would be radian, and this would be degree. So now the remaining solution will now be 540 degrees minus this guy right here, which we approximate this, but let's write it out formally. So this will be 360 minus inverse sine, put a little 1 there, 4/5. And so now when we subtract this, we know that's 180. So this is going to be 180 degrees plus minus minus inverse sine of 4/5. So that's the second solution. So let's go to our Google. And of course, we're just going to be lazy and stay in degree mode. So we're going to say 180, or you can just write the 540 and not do all the additional work that I did, plus inverse sine. So we have inverse sine of 4 divided by 5. And that gives us the 233, and we'll round to 1 decimal. So 233.1 degrees. Now you're thinking, I have to do this every time. No, I just basically proved Professor Ron's lemma. And that's what I wanted to show you, because I did this scratch work here before class, right here, and thought, well, that'll be a quick proof of this that won't require anything fancy. So how do we do this? Okay, so once we find the one angle from the inverse sine function, that's going to give us the one in the fourth quadrant. So we can find the second one by simply subtracting that solution that we got right here from 540 degrees, or if we're in radians, 3 pi radians. So this is one part of Professor Ron's lemma. So just to kind of, that's why the inverse trig functions are important. So now you see, if you need to solve a particular sine equation, just a plain old sine equation, or then we'll do a plain old cosine equation, you see that if you've got the negative here, the lower arc, so to speak, of the unit circle, then to get the two solutions, you're going to do the inverse sine of this, okay? And then you're gonna correct it, okay? You got to correct it to get it in the fourth quadrant with a positive angle or positive radian measure like we did here. And then once you get this value, which is this right here, you can subtract that, as we proved here, from 540 degrees or 3 pi radians. So you're thinking, well, I'm Professor Ron, I'm not going to write all this again. I'm just going to say 540 minus this, but don't round. I mean, if you do it exactly like I've done here, you don't have round off error, which is better. And so boom, there you have it. So now you're thinking, okay, when I've got to solve this kind of equation in the lower arc, by virtue of the definition of the sine function, I'm going to get two. I'm going to get two answers. I'm going to get two solutions. But that won't be the case with the cosine function, as we've already seen. So basically now, let's just go ahead and summarize that. And then we'll do, since we're going to have to do the law of sines, I wanted to do this one first. And then we'll do cosine later, because it's so much easier. So here is a recap of what we just did. Recap. So what we're interested in is solving, in this case, say sine, and I just wrote sine x equal b. And in the first case, we'll have upper arc. So we'll say 0 to pi, or 0 degrees to 180 degrees. We'll say first solution is x, and we can do the same thing. Second solution, we'll just do pi minus x. I didn't prove that when I did the harder one in the lower arc, but it's the same argument. Second solution will be pi minus x, or 180 degrees minus x. So that's the second solution. This is part of Professor Ron's lemma for these equations. And then two, if we're interested in the lower arc, that is pi to 2 pi, or 180 degrees, as I wrote in this problem, to 360 degrees. We'll have a first solution, let's call it x. So this is the one that you figure out. The first solution is the one you figure out with inverse sine. This is the inverse sine solution, and then corrected to the correct quadrant, or sine. That is, if we want it to live in a positive realm like we have here. And then the second solution, as we just proved, will be 3 pi minus x, or 540 degrees minus x. I actually set this out the first time I taught as a professor at the South Campus when I graduated from A&M. and we were doing the Teague Trigg book, and they didn't have this written up in the book. So I said, kids, I've got to come up with a way to do this, because you can't just, ladies and gentlemen, you can sketch something to kind of motivate the logic, but the sketch is not a proof. And if you don't have nice numbers like we have here, if you don't have this result, then what is your answer? You're just kind of walking around with blindfolds on. So I developed this theorem, and it's actually my own, and I call it another Professor Ron's lemma. But the student, one of the students, a young lady, she said, Professor Ron, how do you do that? Well, how'd you prove this? And so at the time, I used the subtraction formula for the sine function, because that was the easiest way to do it. I said, this makes sense, so let me do it this way. But then as I started teaching at the North Campus, I thought, well, the kids haven't had the subtraction formula yet. So I need to come up with another way to motivate this that only uses what they know. And that's what I've done here. So what I was scratching around here, this was just scratch work from this morning, where I thought, well, let me give them a rendition I've used before, and let me get my thoughts together. So the idea now is that we have a nice way to solve the basic sine equation in the upper arc and the lower arc and get both of the solutions, unless you just end up on the axis and then that's it. The axis is the easy part. If you have 1 or -1, there's only one of those. And so that's easy. When we're in the quadrants, we're off the axes, and that's where the complication arises. Okay. So I just wanted you to be familiar with that and know that life is actually good to us. Now you're thinking, well, what can we do additionally with inverse sine functions? We can use some triangles. So for instance, now here's a nice WebAssign problem, and we might say compute. Here's an example. Let's compute the cosine of the inverse tangent of 12/5. Now, when you look at this, you're thinking, well, this is kind of like what we did before in chapter 5, but that was something we were familiar with, like 1. And then you could say, well, the inverse tangent of 1 is pi/4, and cosine of pi/4 is 1/√2. That's fine. And that's what you already know how to do. Again, some of you will send me emails or WebAssign messages. Oh, I don't get this. I don't get this, Professor Ron. This is too difficult. I'm like, no. This is easy. Just do it in order as you come to it. But when we look at this, we say, well, this is certainly defined because that's a real number. But how could we actually write down an exact solution here? Well, we can use the interpretation of the right triangle here, or we can use Pythagorean identity. But so what we want to do here is think of this as the reverse path. So what we can say is use your favorite variable. I don't know, we'll use X or theta. Theta is usually comfortable when we're talking about triangles. So we're going to say let theta be the inverse tangent of 12/5. And then, of course, if we go back to the original stuff, if that's true, then we can take tangent of both sides and think about a right triangle. So then we can say the following. Equivalently, so this is really easy, and now you're going to see how pushing the right triangles on the inverse trig functions are giving us another layer of computational ability. So we have tangent theta equals 12/5. So that just, you're thinking now I can use the Pythagorean identities, which is fine, but that's too difficult. So what we're going to do is think about this particular problem based upon a setup that makes it actually kind of easy. So what is this? What is this? We can think triangle and do Pythagorean. We do it 2 ways. This is just y/x, right? This is y/x. And so if I do this, then I could think, oh, okay, this comes twice like this. Well, the 2 ways will be just really 1 way. So I'm thinking, okay, here's my theta. So I have opposite over adjacent. So I have 12 over 5. And so now I just need, this is where the Pythagorean identity comes in and say, well, I just need the hypotenuse. So whatever I have here, this would be 12 squared plus 5 squared. So that's 144, easy numbers, plus 25. So that'll be a 9, a 6, so that's 169, and that's a perfect square. That's 13 squared. So by the Pythagorean theorem, the hypotenuse is 13. So this gives us exact computational ability. So now we can go back up here and say, well, cosine of the inverse tangent of 12 over 5 is really just cosine of theta. And so the right triangle makes it a little bit simpler. And then, of course, this is clearly an angle between 0 and pi over 2. So at least the triangle makes sense. And then, of course, we do adjacent over hypotenuse, and we just get 5 over 12, and we're done. So that would be a way to actually do a composition where this input was not something that we saw in a terminal point on the unit circle. When this is a terminal point deal, then you're fine. You can say, oh yeah, I know what that is. I can use the unit circle. But when we don't have that, we can use the connection between the right triangle ratios, or you could just forget the triangle altogether and just use the Pythagorean identities. I mean, you'll get the same answer. Everything still works the same way as it did before, but students like the triangles. The triangles are convenient, and they make tabulation of this type of computation very simple. It's like, okay, well, I'll just think of this as opposite over adjacent, y over x, and draw a triangle and finish it off with the Pythagorean identity or Pythagorean theorem, and then boom, what? Adjacent over hypotenuse. So this is easy. This is easy with the triangle approach. So you will use this heavily in calculus too, when you do trigonometric substitution. So this will be a technique, again, that you'll use in the calculus sequence, albeit very simple, but almost kind of miraculous when you think about the computational ability we have when we introduce the right triangles to make it simpler. Now, another thing that we can do is take this idea and do an algebraic expression, just to finish this off before I quote the law of sines. So now we can do a same procedure, that is write, and this will be the same thing, write an algebraic expression for another composition. It's going to have the same thing, but instead of the number here, we're going to have a variable. So we want something like this, but with an x in it. So write an algebraic expression for, I just made this up, secant of inverse sine of x. Now, again, when you think about this, we're doing the same thing. We can just use theta. So we're going to do the same construct. So now we can say what? X is equal to sine theta. So we say, okay, x is x over 1. So x over 1 equals sine theta. So if theta is inverse sine of x, then x, or x over 1, is sine of theta, just like we did here. And then you're thinking, well, okay, I'll write it this way. Sine is just opposite over hypotenuse. So that can help you draw the triangle. And since we've already used the letters, don't try to reuse those. So this will just say, okay, well, I'm good at triangles, Professor Ron. You know, the proof of Professor Ron's lemma with the sine, that was a little bit more complicated, but easy to remember. So now we have theta. So we have opposite over hypotenuse, x over 1. As long as you preserve the ratios, it doesn't matter. You could write 2x over 2. It's still equivalent, but unnecessary. And so now we're thinking, well, that's like what we have here. Now by the Pythagorean theorem, we get 1 squared minus x squared square root. Again, select the positive square root. And so we get 1 minus x squared. Again, we just say 1 squared minus x squared is this leg squared. And to get the leg, we take the positive square root. So again, the Pythagorean theorem gives us this. So this really, let me just kind of outline this in red, since that's what we came up with, like we came up with the 13 there. So this is basically 1 squared minus x squared. In this case, is the adjacent side squared. And so we select the positive square roots. So the adjacent side will be the square root of 1 minus x squared, right there. So now we're done. So this equals, this is so simple, I should have started with this. Secant theta will now just be the reciprocal of the cosine. So this will be 1 over the square root of 1 minus x squared. And so you're thinking, wow, how simple is this? Well, this is very useful when you're doing a trigonometric substitution and you're trying to write a bunch of trig functions in terms of the original variable. So again, this won't be something you're going to do right away in Calculus 1. But when you get to Calculus 2, boom, all those inverse trig functions just are thrown in your lap, so to speak. So that's why you have to learn this now, so that when you get there, I mean, it can't just be just-in-time teaching. I mean, you can't take calculus and then your professor says, okay, I'm going to teach you trigonometric functions, inverse functions in 5 minutes. No, 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 that doesn't work. You'd never make it. So the idea is that we develop pre-calculus to get you ready for the foundational material that you're going to have to utilize when you study the calculus of the inverse trig function. So you have to know what they are before you start trying to take derivatives of them. This is essential. So again, this will be a fun concept in Calculus 2. So there we have it. So the inverse trig functions are actually turning out to be very useful for us. Now, the next topic is called the law of sines, and you might be thinking, well, do we need to spend a lot of time on triangles? And the answer is no, but the computational aspects of the law of sines and then of course the law of cosines are useful, though they're not the focus. We could spend the same amount of time just going back over inverse trig functions and that would be fine. But when you take physics, it's great, and engineering, it's really useful to know the law of sines. If you're going to be a surveyor, yesterday during conference hours, I couldn't come up with the name surveyor. And then finally, one of my students figured it out. It's like, we were like, what, a landscaper? Surveyor. Because the surveyor is the person who measures things. You know, you have the ATS and all these equipment where you measure angles and distances, and you use your trigonometry to help you with the computations. So the surveyors really do use the inverse trig functions. They use the degree measure. They live for that. So maybe what we're talking about now is a little bit tangential. It's still important stuff that you will need in engineering and physics, not so much in the calculus. So we're going to say law of sines. And this is actually easy to motivate. Law of sines. So what we're going to do is start out with a generic triangle because we're lazy. For instance, when you want to solve a triangle, a general triangle, solve a triangle, when is it possible? I like the way Dr. Stewart does this. You can have 4 hypotheses that will allow you to solve an arbitrary triangle, even if, well, and maybe it doesn't even exist because it makes no sense mathematically. So you can have what they call angle, side, angle. If you've got that hypothesis, you can solve a triangle. 2, if you have side, side angle, this is called the ambiguous case because it uses Professor Ron's lemma that I just showed you, and students don't like it. And then 3, you have the side angle side. Again, if you have that hypothesis, you can actually solve a triangle. And then, of course, you can have all 3 sides. Now, when it comes to the law of sines, the first 2 are workable. That is, you can use law of sines. Now, for case 2, this is what we call the ambiguous case, in the sense that, what does that mean? Well, you know, you could always have bust, you could have no triangle. That is, maybe the hypothesis doesn't even make any sense. That would go for any of them. I mean, mathematically, the inverse trig functions have to make sense when you try to solve for angles. And if you can't solve for angles because the equation makes no sense, then you can't draw it. You know, I mean, that's what I'm saying. The mathematics of the geometry and the actual figure are all related. They're equivalent. So if one doesn't work, the other doesn't work, and vice versa. And then for instance, you could have what we call one triangle, or we all know about Professor Ron's lemma with the sine. When you're thinking of 0 to 180 degrees, you have the possibility of 2 triangles, because you may get 2 solutions to the sine equation, which is what I did right here. Maybe you're solving a triangle and then you get this situation here. You actually get 2 solutions that make sense. And so you definitely, you get 2 triangles. That's what they call it, the ambiguous case, because of course you don't know what you have until you study the hypotheses. And then of course you could have 2 triangles. So this is Professor Ron's lemma. So we'll just say Professor Ron's lemma. You know, what are you going to do? Draw a picture? Ladies and gentlemen, drawing a picture doesn't do the math for you. It just simply helps you organize your thoughts. The pictures are great when you're trying to organize. We like pictures. We like drawing the triangle on the last 2 examples because it helped organize our thoughts, but it's not a proof. Now, what we want to do is like, okay, what's the generic triangle that we want to use? Let's draw it like this, and it's easy if we think of it with double use of the letters, because we're lazy, right? So, for instance, if we think of angle A and vertex A, so A is going to denote the vertex and also that angle right there. And the opposite side we're going to call lowercase a, for that A denotes the side and also the length, like we did before. And then we might have vertex B or angle B and the opposite side lowercase b. That way, if we do things this way, we can even if you have triangles within a triangle and you've got all these letters and know how you say angle ABC and angle DAC, and then you go crazy after a while, you can always label the angle with one letter and avoid having to draw all those letters. I know you remember this in high school geometry. It was always a nightmare to keep up with everything. So it's sometimes easier just to do a simple labeling like this, even when you have a triangle within a triangle. So if this situation is what you have, that is, we have a generic triangle. The law of sines says the following. That is, you can apply the area formula to this triangle 3 times. That is, apply area formula to this triangle 3 times. So you can think of B and C included angle. So we'll say area. So we'll say B and C included angle. So we have 1/2 B times C sine of A. So you see this notation is cheap, but it's efficient. We'll take it. You know, we always have to know context. So if you're using degree mode on your calculator, you need to keep that in mind or make it clear on your paper. There are all kinds of pitfalls in trigonometry if you get sloppy. And I am extremely meticulous with this work. I mean, extremely meticulous, because if I am not, you develop bad habits. And if this is difficult for you, it should be. Trigonometry is difficult when you follow the rules. When you don't follow the rules, you just make it up. And then you're like 50-50 chance. So if you follow what I'm teaching you and you utilize the WebAssign as a means to reinforce, then you're going to learn this stuff and you're going to feel good when you get to calculus, as opposed to getting to calculus and you don't even know what a reference number is. That happens, ladies and gentlemen. So just remember, the time you put in now is going to pay off handsomely later. So now here, let's think of included angle in A and C. So we have 1/2 A times C sine of B. You know, I always have to preach eventually in the lecture, but it's only to remind you of the goal. You're a future STEM professional, and I want you to make a difference in our society because we need you. Now here, included angle C, AB. So you're thinking, if I apply the angle, the area formula 3 times, this is the included angle for this one, this is the included angle, and then this is the included angle, they're all equal because they all define the area by the theorem we proved. But now you're thinking, well, we're done. All the 1/2s go away. So you're thinking, okay, so this is BC sine A, AC sine B, and AB sine C. And so you're thinking, is this the form of the law of sines? Is this the final form? Well, we want to go one step more. We're going to divide each of these terms, the entire equation, equality, by ABC to absorb everything and then get the final version. So this is what you did. This is what you used to do. I never do this, so I thought I'd just treat everybody. I'm just multiplying by the reciprocal of ABC. And so now, what is this going to be? Well, the BC's absorbed, and we just get sine A over A. Everybody loves the law of sines because you can never forget it. It's easy. And then the AC's absorbed, and we get sine B over the length side B. That is sine of the angle B divided by the length opposite. And then here, the AB's absorbed, and we get sine C. That is sine of this angle divided by the length of the opposite side. And there we have it. You're thinking, wow, that's the easiest proof we've done all year. Now, I will say this is all contingent on the fact that you believe the theorem about the area using the sine. So the beauty of this result is that it basically is equivalent to the area of the triangle that we have here. So where did it all start? With the unit circle. So if you burn the unit circle, trigonometry goes away. So we're just looking at it that way. So the idea here is, and let's look at some examples of this. With angle side angle, remember that Euclidean sum is 180. So if you've got two angles, this is one triangle. So let's just note for angle side angle, there's only one triangle. That is, if there is one, there's just one, because the triangle is fixed. Because the remaining angle is fixed, there's no flexibility there. When you only have one angle here and two sides, there's built-in flexibility, which you don't have here. So angle side angle will always, produce one triangle. If the if the hypotheses mesh correctly. Okay, so you don't have to worry about, okay, is there another triangle, whatever. This one you do. Of course, these, they're fixed also, but they're going to require a different theorem called the law of cosines to get those moving. So the law of sines will help us with 1 and 2. So let's do a couple of examples. So you're thinking, law of sines easy, and it is easy. We need easy occasionally. So let's do an example here where we can use the law of sines. And I want to show you how you can do your computation and use your degree mode to keep the computation simple. So here's a WebAssign problem. We have a generic triangle. I'm just going to draw it so you know what it is. And then B and B. And what we're given, here's the hypothesis. The hypothesis is the following. That is, we have angle A is 52 degrees. Angle B is 70 degrees. So we've got this deal here in the angle. So angle side angle. And C is 26.7. So this is ASA. And what we're asked to do is compute. You can solve the entire triangle, but that's really kind of that's something you can do, but it's one of these things where you just pain through it. Very simple calculations unless it's an ambiguous case. So if we want to compute A, we're thinking, okay, this is angle side angle. I've got angle A. I don't know the side opposite, but I do, if I look at this, I've got angle C in the side opposite. So I can use law of sines with angles A and C. So in this case, we can say use law of sines. That's why I did the Professor Ron's limit with the sines, so you could see how to negotiate the angles with the sine function for the ambiguous case. So now when we think law of sines, we've got what? We have sine of C divided by C. Well, let's see. Actually, we have to use B. Sorry. Or actually, we have to use, in this case, let's see, we want to solve for, let's see what I have here. Well, oh yeah, we want to solve for C first, and then this will work. Let me just write this out. Sorry, I lost my train of thought. And then we've got, let's see, sine of A over A. Now, notice this is what we need because we have the C, but our first side calculation will be this. So we're going to say C from this part. The actual angle C will be 180 degrees. We'll use degrees here just to remind us that that's what we're working with. And then we have 52 degrees plus 70 degrees. So we have 180. And here we've got a 2. So that gives us a 122. So 120 from 80 is what? 60. And then if we subtract 2, that gives us 58 degrees. So angle C is 58 degrees. So now we know the C, the lowercase c, but we know the uppercase A, but not the lowercase a. So now, if and only if, let's just go ahead and do the flipping around. So we have A over C equals sine A over sine C. If and only if. You can do this in one step, but just to give you practice working with proportions. So now A will just be C times sine A divided by sine C. You can put a little dot there, so you know that's just not CS, but C times sine of A. And so now we're thinking, again, for ease, think degree mode, so we don't have to worry about doing conversions, even though I've shown you how to do that. This is like the problem we did yesterday. We'll use the convenience of the conversion mode on our Google calculator. So we'll have exact. And again, even if you're given a decimal, this is exact. This is exact. That's given in the problem, so it's exact. I still have students say, well, how am I supposed to know how to round? I said, well, if it doesn't tell you to round, what's my answer? Exact. I'm not really understanding why no one seems to get this, but I'm not going to give up on you. I never give up on my students, even though they give up on me. It's unfortunate, but that's just the lay of the land. So we've got 26.7 times sine of 52 degrees, and then we've got sine of 58 degrees. So now this would be the exact representation for A, but now in this particular case, what did they say? Let me write what WebAssign said: round to 1 decimal. So now we can use our Google calculator in our degree mode. So this is a very straightforward calculation, much simpler than before. But notice here, the interpretation and the sine function actually are good to us here. We only have one triangle. We see that the other angle is well defined. And then when we look at this computation here, this is all well defined. This triangle exists. There's nothing that's been violated with solving equations. So now we're thinking, well, don't we wish all problems were this easy? So now we go to our Google calculator. And so again, make sure the degree is highlighted so you know you're in the degree mode, so it does the conversion for us. So we'll have parenthesis 26.7 times, now we do sine of 52 degrees, 52, close, and then we want to divide by the sine of 58 degrees. And this gives us 24.8097. The Google calculator is very nice, ladies and gentlemen. Excellent readout, beautifully set up, and it's free. So, you know, I'm not doing the lockdown browser now. I may eventually do it, but I want you to be able to use the Google calculator. So, you know, just keep that in mind. So we have 24.8 to 1 decimal. So when you think about this, this is a mode of solving for the remaining components of a triangle. So for instance, here we see we've got C, we've got A, we've got B, the uppercase B, uppercase C, uppercase A, and then the only other thing we would need would be the lowercase b if we wanted to completely solve the triangle, which again, you can just use another application of law of sines. So the key here is that when you want to reuse something, I will recommend that you run your answers to several decimals so that you can round to 1 and not have round off error. That way everything is good. You don't worry about being off a decimal place or whatever. That's one thing where the Google calculator is a big plus to our understanding, and it helps us to present a reliable approximation that we may need for our clients. Say we're surveyors and we have to keep our clients happy, so we get paid at the end of the month. Now, let's look at another example. So let's go back to excuse me. So here's where I finished. I start talking and I should go back to this. Notice we've completely solved, and then we can solve for B if you want. So the idea here is that the law of sines is very user-friendly, extremely user-friendly. Now, let's look at an example This particular example, again, I talk to my students. I said, I know that I don't like WebAssign because of the videos. I know some of the videos are interesting and they don't always use my methods, but they give you a different perspective. But sometimes the perspective is somewhat cumbersome and not based on the best kind of mathematics. But the key to the WebAssign is the beautiful problem sets and the MATLAB backbone and my ability to be able to fashion problems the way I want. That's the amazing nature of the WebAssign. I was telling one of my students, I said they could pay Professor Ron to make videos, but they wouldn't be able to afford me. So what I do is I come to Sanjak and provide you all with the good videos. So what we want to do in this case, this is what I talked about first. We want to label this problem so that we don't go insane. So I'm going to give you a perspective which is based on how I've taught you. So here's what we have. I'm going to draw this figure. So it's going to be a triangle within a triangle. So one of the triangles is going to be isosceles. So we're going to do our best isosceles. So this is going to be isosceles, not Rembrandt, of course, but you know we'll use our imagination. And then we're going to connect to make another triangle. So we're going to have C, D, and I'm going to show you what's given. A. I think that this is D. That I don't really care about it because I'm going to label it. And we're given the following. I'm going to call this triangle 1, and I'm going to call this triangle to the right triangle 2, like I've done before. Here's what we're given. We're given that this side length is 19. And why do I know it's isosceles? Because this side length is also 19. So this side has length 19. This side has length 19. This side here has length 27. And we're given a 30-degree angle here. Okay? This is what's given. This is the hypothesis. Now, the WebAssign goes a little insane and says they want you to compute this angle and this angle. So that would be angle BCD and angle DCA. Ladies and gentlemen, if we have to write that down many times, then we're going to go crazy. So I'm not doing that. So I'm going to label them with nicer labels. So what I'm going to do, I'm going to call this angle here alpha, because I'm going to be lazy and we're going to refer to that angle as alpha. And this angle here, we're going to call beta. Use your favorite Greek letter. You can always use, I mean, here's the thing. You want to use the letters in the problem if you have to type something algebraic. Okay, that's fine. And so you remember that, but as you're working the problem, if you need a little bit more convenient notation, that's fine. But we still have to adhere to the letters that are given in the problem if the problem requires an algebraic expression. So remember that when you do these algebraic expressions for the compositions, you want to use variable x if x is in the problem, not a t, because then WebAssign won't understand it. So here's what we want. This is what WebAssign says. Compute alpha and beta. Now, when you look at this and you think about this problem, well, this is tailor-made for law of sines. And of course, I'm going to do them in the order that I think is most efficient, even though others may look at it differently, and you're welcome to do that. But notice here, this is tailor-made. So notice what I'm going to do first is I'm going to just say 2 for triangle 2. And here we see that we have angle A and its opposite side. And then this angle, because I'm going to be lazy, I'm going to not call this angle CDA or whatever. I think I'm going to label this to be theta. And then of course, this is an isosceles triangle. So these base angles are congruent. So I'm going to call them phi. So I'm just going to use nice little Greek letters to keep us sane. So you can add these all over the place to keep your life copacetic, so to speak. Now, notice what we have here. We've got this obtuse triangle here. So we've got the shorter side here and a longer side here. So when we actually compute this angle, it's not going to be the angle that we get from the inverse sine, because that's going to be between 0 and pi over 2. That's too small. So we're going to have to make an adjustment here using Professor Ron's lemma to get the obtuse angle. And again, I can't really reason from the picture, but when I look at the numbers here, the numbers don't support that the theta would be between 0 and pi over 2, or 0 and 90 degrees. So I'm going to have to make that adjustment there. So that's why this is a really good problem. So now we see that we have sine of 30 degrees. Again, picking on A and its opposite side over 19. Oh, good, a nice angle, 30 degrees. It's like WebAssign is just being too kind to us. And then we have sine of theta, because Professor Ron's being lazy, with opposite side 27. So now we can solve for theta, that is solve for sine theta. So sine theta will just be 27 times, well, sine of 30 degrees is 1/2. Well, hallelujah, something simple for a change. And then divided by 19. But of course, now we can bring the 2 downstairs and hit that with the 19. So that'll give us what, a 38, right? So now when we look at this and we're thinking, okay, well, what is the angle we want? Notice, theta will be the inverse sine of 27 over 38. Again, we're going to use our degree mode, at least thinking about this in degrees. And then, or we can write it in terms of the conversion factor. Let's just think degree mode to keep our lives, sane. And I think you appreciate that using the Google calculator. Now, of course, this is the acute angle, So this implies, and this is where you kind of run into issues here. You think, okay, well, this is really a theta. It's not really the theta that we want here. So when I put my theta here, I'm just going to call this a theta 1, because it's really not that theta. I'm going to call this theta 1. Now I can go back and say that's theta 1 because that's the angle in the first quadrant. I want the one over here. I want Professor Ron's lemma for the second solution. So this implies that theta will now be 180 degrees minus inverse sine of 27 over 38. That's that angle right there. So the key here is that we have to think about this as being a computation that respects the arithmetic here. So we need the obtuse angle. And so now notice, if we add all these angles, we get 180 degrees. So that's exact. So this implies that beta will now be 180 degrees minus the other 2. So that'll be 30 degrees plus 180 minus inverse sine of 27. This is a beautiful problem. That's why I love the WebAssign. Dr. Stewart has crafted some beautiful problems, and that's why I like his book. Not a perfect book, but no books are. So now again, remember degree mode. So now we use the angle sum to add them all up. And so now 180 minus 180, that's 0. So this gives us plus. So we get sine, inverse sine of 27 over 38 minus 30 degrees. So remember, the minus is plus. So this is beta right here, and this is exact. Now, most videos aren't going to do it this way. I do it this way because I'm a mathematician. Somebody who's doing the video just might be a math student who's, needs a part-time job, and WebAssign's got to, save money. So they're not going to spend a lot of money on the videos. You're spending money on the algebra system that they create and maintain, which if they were really charging us, we couldn't afford it. So I have to thank Cengage and North Carolina State for making available a complex computer algebra system that's going to help my students get better. So now I can go, here's exact, this is exact. So Professor Ron and his students can go to the Google calculator in degree mode and get beta. So let's do it. So let's go to Google. So now, again, degree, DEG, make sure that's highlighted. So we have inverse sine. So arc sine, so we'll do 27 divided by 38 minus 30 degrees. And this gives us 15, excuse me, 0.2777. And then in this case, what did WebAssign say? Round to 1 decimal. Round to 1 decimal. And so that'll give us 15.3 degrees. Excuse me. So what we're seeing here with this type of example is we have a very straightforward application of the law of sines. Again, I'm working with the part of the figure here that's easiest to start with. Now, I mean, we can use this to get alpha over here. So for triangle 1, notice that this, when we look here, these are supplementary angles. So phi is theta 1. That's a freebie. Phi is theta 1 because these are just supplementary angles. So we're done with that. So we're going to say observe. It's weird how if you just actually look at these problems are simple, but again, you just have to let your mind absorb what's going on and then process. So phi is actually theta 1 because they're supplementary, and that in degree mode is inverse sine of 27 over 38. And so now this, talk about a gift. We have an isosceles triangle, so we have 2 times phi plus alpha equals 180. I mean, how simple is that? We haven't had to do any rounding anywhere. I mean, we've got a problem that's tailor-made to symbolic computation. So now this implies that alpha will now be 180 degrees minus 2 times phi. So we get 180 degrees minus 2 times, I'll put a little dot there, inverse sine of 27 over 38. And I'll put the little parentheses there so you can see that. So again, this is important, everybody. I'm trying to set this up so it's user-friendly. I've shown you how to do the conversion factor, but again, we're in degree mode. So when you're taking a quiz or a test, the degree mode's going to save you some time. This part is the mathematics. And then, of course, the mathematics of using the Google calculator right now is just a luxury. We like using the calculus and the technology to combine to give us nice approximations. So here, this is exact. This is the exact value of angle alpha. Hard to say, angle alpha. And so now we'll go to our Google calculator to get a nice calculus approximation. So let's do that. So here, back to Google. You're thinking I should have saved some of this. So this will be, again, DEG, degree mode, 180 minus, and then we'll have 2 times inverse, INV, inverse sine of 27 divided by 38. And this gives us 89.444 approximately. And we want to round to 1 decimal and we get 89.4 degrees. So I thought this particular problem, ladies and gentlemen, was really neat because it showcases all of the neat things about the law of sines, and also utilizes Professor Ron's lemma in a way that makes sense. So the sine equation is actually a little bit complex when it comes to these theorems, because the way they're set up, you have to think about the way we restricted them, because the inverse sine will give us values between negative pi over 2 or negative 90 degrees and positive pi over 2 or positive 90 degrees. And when we're dealing with positive inputs, that just restricts us 0 degrees to 90 degrees. So the output for these triangle problems will be acute angles. And we have to make sure that the mathematics of the problem gives us the angle that we need. And so this is where we have to work a little bit harder using Professor Ron's lemma, but at least it makes sense. So excellent problem and a good learning problem. Now let's look at another example. I thought this was an interesting little problem. I don't think that, don't forget your Pythagorean theorem and your fun problems and stuff. You're good at Pythagorean theorem. You learn that in 5th grade probably. That these days that you all are as smart as a 5th grader, because that show was based on you all, and it seemed as though 5th graders were geniuses. So what this problem does in this particular case is it gives us a tree on the side of a mountain. Basically, we have this slope. This is a neat example. It's a word problem. So you've got this slope, and you've got a tree here. I'll just say here's the tree right here. You got this tree, and it has a given height. We're going to call it H. And you've got the sun shining right up here, and it creates a shadow. So it creates another triangle. So to the top of the tree, right here. So you've got the sun up here shining, and it creates a shadow, and the shadow length is right here, and the shadow length is 230 feet. 230. So we'll say shadow 230 feet. And then with the horizontal, you have 2 measurements here. That is, you're given that the slope with the horizontal is 26 degrees. And you're given that the slope with the horizontal and the actual casting here of this side of the triangle is 56 degrees. So this angle is 56 degrees. And then of course you can just go ahead and dot through here to make a right triangle. So we're saying here slope with horizontal corresponds to 26 degrees. And then we have, again, how the light beam here. So we'll say light beam, even though you can't probably see it, light beam with horizontal. And the light beam makes the shadow is 56 degrees. That's what's given. This is what we call the hypothesis. And of course, WebAssign gives you a nice, beautiful little picture, and mine's pretty terrible, but it'll do. So you're thinking, what are they going to ask us here? They're going to say, what's the height of the tree? What is the height of the tree? Now, of course, if you're a surveyor, then this problem would be something that you could figure out pretty quickly. But since you're in Professor Ron's pre-cal class, you can do it too. So notice we've got this triangle here. Notice this is 90 degrees here. Let's just go ahead and write all this in. This is 90 degrees. That's a right angle. And then of course we've got 56 minus 30, or excuse me, minus 26. That gives us 30 degrees here. And so now we're thinking, well, how do we get the rest of this? So we're thinking, okay, so we've got this big triangle here that is, notice, 56, 90, and that's going to give us this angle up here. So observe, and I'll label this. I'll just call this, I'll call this angle beta. Observe, beta plus 56 plus 90, all in degrees, equals 180. That is, if you look at the big triangle, so I'll just say large triangle, the large triangle. So now beta will be 180 degrees minus, so we'll add these up, that'll be a 6 and a 146. So that'll give us what, 34 degrees. So now we can write up here beta equals 34 degrees. Now, of course, these calculations are simple, but they set up the law of sines. So when you're given a story problem like this, you draw the picture and then you just say, well, I need some angles and I need some sides. So what do I have here? What do we have? We've got the angle here and the opposite side length. That's good. And then we had the angle here opposite H with one unknown being H. And so that's law of sines. So basically, when we look at this, we have what? We've got a setup that's good to go, an angle side angle, so to speak. So now we can solve this problem with no issue whatsoever. So by law of sines, we'll say angle 34, sine of 34 divided by 230, degree mode. So this is a nice little simple problem once you set up all the particulars. And then we have sine of 30 degrees. And in this case, we have the H divided by H, the opposite side. So now let's do our little calisthenics. So we'll replace the H and the sine 34, flip those around. So we have H over 230 equals, well, and sine, we know what that is. Sine of 30 is 1/2. That's easy. Divided by sine of 34. Again, degree mode. So if and only if the height of the tree will now be 230 times 1/2 divided by sine of 34 degrees. And then we can bring the 2 downstairs, or we can divide, it doesn't matter. So here this gives us a 1, and then a 2, that gives us a 1, so a 115. over sine of 34 degrees. So this is exact. This is exact. So again, degree mode. So now we can go to our Google calculator. This is a good one to stop with. Again, very simple. So we have 115, again, DEG, degree mode, 115 divided by sine. So that you see this theorem is great. If you do surveying, this would be a very nice theorem to know. And this will give us approximately 205.65. And then in WebAssign, they say round. Let me write this out. Well, let me just say 6535. Let me go back to my document cam. And so they say round to nearest foot. So this gives us 206 feet. Now the problem itself is a little bit wordy, you know, but the idea is that using basic construct of the Euclidean triangle, what do we use over and over and over and over and over again? Supplementary angles sum to 180 degrees or pi radians. The sum of the interior angles of a Euclidean triangle is 180 degrees or pi radians. We use that over and over. And what's the measurement of a 90-degree angle? Well, 90 degrees, obviously, a right angle, pi over 2 radians. So we use basic ideas that you learned as a 5th grader. But the thing is that now we've taken it to the next level where we have all of this extra stuff like the law of sines, and then Professor Ron's lemma for solving sine equations. But when we look at this, all of the mathematics is supported very beautifully here. No problem with having to solve equations. Everything is nice and defined. We don't have an issue. So when you do the side-side angle in your WebAssign, you'll see that either you'll get no triangle, 1 triangle, or 2 using Professor Ron's lemma. So I hope that the law of sines has been kind of a little bit of a fun trip for you in the sense that we've gotten a little bit away from some of the mundane nature of the inverse trig functions, but we see how the inverse trig functions paved the way to understanding the law of sines and how we work with these types of problems. So maybe this will give you a nice breather. Now, of course, by tomorrow, I will post a announcement that'll give you additional details about the upcoming test. And so I appreciate your attendance today. Enjoy the cold weather. It's cold. You know, if you like it, great. If not, it will change. And good luck with your studies. And if I don't see you at my conference hours, I will see you next week. So thanks, everybody. Have a good day.
Have a good day, sir.
Thank you.
Bye. Thank you, everyone.